Welcome. In this lecture, we will continue our discussion with paging. We have looking at schemes to improve the performance of paging. In this, we looked in the last lecture, we looked at page replacement algorithms, where better page replacement algorithms improve the performance of paging. Then we looked at the scheme of page buffering, which is related to the issue that when during replacement, when we have to write to a dirty page, that dirty page has to be first written to disk, and the system has to wait for this dirty page to be written out to disk, and then only the page that is required can be brought into the memory frame. Now, to avoid this waiting time, we keep a pool of free pages at any point in time. So, when we need to replace, we as before we select a victim page. If that page is dirty, we will write it to the disk, but what we do is that instead of writing to this dirty, we select the victim page, fine, but before writing this victim page to disk, that victim page, if it is dirty, to disk, what we do is we select a page from the free pool and allocate this for replacement, and therefore the system does not have to wait for this frame to be, for the victim page to be written to disk first before replacement. So, whenever there is a replacement, I choose a frame from the free frame pool and allocate this for replacement. Now, after I have given this and the data has been written from the secondary storage into this frame in the free frame pool, and the process has been restarted subsequent to service of the page fault, then the IO channel is free again, and then what we do, this victim page is written to the disk, and then after this victim page is written to the disk, this page, the modify bit or the dirty bit for this page is again reset, and then this frame is again added to the free frame pool. Now, this basic scheme was an extension to this basic scheme is that what we do is that whenever the IO channel is free, I find out a dirty page and I write it down into the disk. So, I maintain a queue of all the dirty pages that are currently there in memory, and whenever the IO channel is free, I slowly when the IO channel is free, I write it down into the disk and add these pages into the free frame pool. Another small extension to this scheme is that, so whenever I have written a page, a dirty page, so in the previous scheme we saw that I took a dirty page and I wrote it onto the disk in my free time, and then I added it to the free frame pool. Now, I have added this to the free frame pool, I have added this frame into the free frame pool, but when I have written, I have not destroyed the contents of this frame. I have written the contents of the frame into the secondary storage and I have reset the dirty bit, fine, and I have also added this page frame into the free frame pool, but this does not mean that I have destroyed the contents of this page. So, therefore, if it so happens that my processor needs a page which is there in the free frame pool, and then instead of going to the storage, I can directly take that page from the free frame pool itself. Again this issue, what we are trying to say is that I have a page for which its dirty bit is on. Therefore, according to the earlier scheme, when the IO channel is free, IO processor is free, I have written this page into the free frame pool, into the disk, and then I have added this page into the free frame pool. But addition of this page frame into the free frame pool does not destroy the contents of this page. So, by chance during subsequent accesses, the processor needs this page. This page is there in the free frame pool. I directly take it from the free frame pool. I do not have to go to the secondary memory, and therefore, I save a page fault. So, whenever I have to access after I will see the free frame pool first. if the page is there in the free frame pool, I'll take it from there itself instead of going to the disk. Then we look at schemes for allocation of frames. Till now we have been looking at schemes where I have the entire set of frames in the memory, and any page can be replaced by any process. So, I have a global set of frames, and the replacement algorithm will search from this global set of frames to find a frame for replacement and give me. Now, this may hit the performance of processes. So, to avoid that, what we do is that we often allocate a minimum number of frames to each process. So, each process needs a minimum number of frames. Now, why does it need? For example, to execute an instruction, it will need one page in which the instruction is there. It will also need data. It may need to read data. It may need to write data. So, whenever it needs to read data, it will have to read from data from the pages in memory which contain that data. So, these pages corresponding to this process have to be kept in main memory. Page which contains the instruction needs to be kept in memory. The pages which are there which contain the data needs to be kept in memory, and the pages where the data needs to be written to needs to be kept in memory. So, therefore, there is a minimum set of active pages with which a process is at any time is working on. This set of active pages it must keep in memory. So, therefore, each process at any given point in time will require a minimum number of frames to be allocated to it, because these frames will contain the pages, active pages that this process needs at any time. If these minimum number of frames is not given to the process will frequently page fault. Okay. So, to avoid that, each process must be allocated a minimum number of frames to ensure a minimum level of performance. Now, allocation schemes are typically of two types: fixed allocation and priority based allocation, and there are many variations of this. In a fixed allocation scheme, what happens? Suppose this is basically equal allocation. For example, if you are given 100 page frames, and we have 5 processors, we give 20 frames to each process. So, just you know the number of processes and you know the number of frames divided by number of processes, and therefore, that many frames is allocated to each process. Okay. So, in addition to this, you can keep some free frame buffer pool for each process. Now, as against this equal fixed allocation, we also have proportional allocation. So, what does proportional allocation do? It tries to fairly allocate frames to each process based on process size. So, what we are trying to do? We are trying to find out how many frames should be allocated to each process. The first one looked at fixed allocation, where all processes gets depending on the degree of multiprogramming, depending on how many processes can coexist together, co-execute together in the processor, and so that many processes need to be kept in main memory. When I know this, therefore, the degree of multiprogramming, I divide the frames equally among these processes irrespective of the characteristics of each process. Okay. So, therefore, if the process is big, a small process which requires a small number of pages at a given time, and a big process, let us say, which requires a large number of frames at a given time, will get the same number of pages. So, the small process will do very nicely, and the large process may be doing bad in performance, because the large process has an insufficient number of frames allocated to it, whereas the small process has surplus frames allocated to it. So, the small process does very well, but the large process does not as well, because the number of frames allocated to it is not as it requires. Now, to overcome this problem, we looked at proportional allocation. What do we do in proportional allocation? We allocate the frames to processes based on the process size. Okay. This is dynamic. This is dynamic, as the degree of multiprogramming process sizes are subject to change. The size of a process, that means the size of a process in main memory at a given time, will vary in time. The degree of multiprogramming, that is the number of processes that are co-executing together in the system at a given time, will also vary. Therefore, the number of frames allocated to a process will also vary in proportional allocation. For example, let us say m is the total number of frames that are there in memory at a given time. Let Si be the size of process Pi, okay, and S is the summation of the size of individual processes. So, the size of process in terms of the number of pages it requires. M is the total number of frames, and how does this allocation, how many frames will process Pi get? It will get Ai number of frames. How is Ai calculated? It is calculated as small si, the number of frames it requires, capital S divided by capital S, the total demand for S, into m, the total number of frames available in memory. So, let us say if we have two processes, the first one requires 10 pages, the second one is a big process, requires 127 pages. So, capital S becomes 137. So, for the first process, the number of frames that the first process P1 will get will be A1, and how is A1 calculated? 10 divided by 137 into 62 equals to 4. Okay. Why 62? Because say, let us say we have allocated 2 frames for the operating system, and the rest of the frames are allocated to user processes, let us say. And then how many frames will the second process get? The second process will get 127 divided by 137 into 62, which is approximately equal to 57. So, here we are allocating frames based on the sizes proportionally. We are allocating frames proportionally to processes based on the size of the processes in terms of the pages it requires. Now, the use of a priority based allocation scheme using now it may so happen, now when we are using this priority based allocation scheme, we are ignoring priorities of processes. Now, we may so want that we will allocate a higher number of frames to a high priority process while making low priority process suffer. Because if for we want higher performance for the high priority processes with respect to the low priority processes. Now, to take care of this, we can use to allow this such priority based allocation, what we can do is we can use a proportional scheme using priorities. That means, instead of process sizes, instead of the sizes of processes in terms of the number of pages it requires, we can proportionally allocate frames to processes based on the priority of the processes. So, if you proportionally allocate based on priorities instead of the sizes of the processes, we are doing a priority based allocation. However, if we are only doing a priority based allocation and looking at nothing else, we are completely ignoring the size of the processes. So, we can also do a priority based proportional allocation based on a combination of priority and size instead of going aggressively for only priorities. So, a combination of priority proportional allocation of frames to processes based on a combination of priority and size maybe will balances both priority as well as the requirements of the processes. It takes care of both the priority of the processes and the requirements of the processes in number of frames. It tries to look at both ends and do a better allocation. Okay. So, this is all with priority based allocation. The other issue to look is doing a global versus local allocation of frames. Now, in a local frame allocation, we said that we have allocated till now, the discussion that we have been doing deals with this. How many frames will I allocate to each frames? Let us say I have allocated a certain number of frames to each process currently under execution. Now, how will the replacement work in this scenario? Now, there are two replacement schemes. There are two ways to look at replacement after we have allocated frames to each process. One is local replacement, in which page replacement will only occur within pages which are allocated within frames which are allocated to a given process. So, let us say I have a process P1 and I know that I have allocated a set of 10 frames to this process. Now, during replacement I will only consider these 10 frames when I am doing a replacement. I will not consider for allocation frames allocated to other process for this process. This is a completely local replacement strategy. That means, when replacing I will only consider pages of this frames of this process for replacement. Against global allocation, what will I do in global replacement? So, during replacement I can look at the entire set of processes that I have and choose any frame for replacement for this process. So, let us say in global replacement I have a process P1, and then what happened, this P1 has done a page fault and I require to replace a page. While during replacement I will not see whether I will not replace this page into a frame of P1, I may not. I will consider all frames in my entire memory and I can choose any frame for replacing this page, and then this frame will come into P1. So, P1 has done a page fault, P1 contains a set of 10 frames. Now, in global replacement I am not considering that I will only use one of these 10 page frames for replacement. I will consider all frames that are in memory at a given time and I can choose any frame for replacing this page, and after this frame will now be added to the frame pool of P1. Okay. So, this will happen in global replacement, in completely global replacement as against completely local replacement. A third strategy is this, a priority based third strategy is this. Let us say if a process Pi generates a page fault, select for replacement one of its frames is available. So, this is local replacement. So, you try to do a local replacement if you have a free frame in your, if you have a free frame in the pool of frames that are allocated to Pi, use that frame for replacement. If you do not have a free frame, what do you do? Otherwise, you try to select for replacement a frame from a process with lower priority number. So, this process Pi has a priority or importance. Either you try to get a frame local replacement from a frame of this process, or you choose a frame from a process with lower priority. What does this allow? It allows a high priority process to increase its frame allocation at the expense of low priority processes. Now, when you allow this semi global allocation, what you basically do is that the number of frames after you do this replacement. So, basically you are stealing a frame from a lower priority process after replacement, and after replacement this stolen frame will be added to the frame list of Pi. So, the number of frames which are allocated to the lower priority process reduces and the number of frames allocated to Pi increases. So, therefore, using this scheme allows a high priority process, say Pi here, to increase its frame allocation at the expense of low priority processes. Now, we come to the next issue, which is thrashing. Now, we are saying that, as we have discussed, each process requires a minimum number of active pages when it is executing at a given time. This is required for the instructions. So, the pages that it requires for the instructions that it is executing, the data it requires for these instructions, and the data it requires to write to. So, these active pages is at least required for the at a given time. So, these active pages are required by the process, and this the number of active pages that will be required by the process at a given time is a characteristic of the process itself. How it is using data and how it is using how it is executing data, how it is executing instructions at a given time, that will determine the number of pages that it requires. Now, we said that we have allocated a certain number of frames to each process. Now, if a process does not have enough pages, then page fault rate becomes high. What do we mean by does not have enough pages? So, in the frames that are allocated to it, so sufficient frames are not allocated to this process for its active pages to be in memory. That is why we are saying that the process does not have enough pages in memory. So, if it does not have active pages, if it cannot keep all its active pages in memory, then the process will frequently page fault. A page that it requires is not there in main memory, and therefore, it has to be brought from secondary memory. Now, we need to do a page fault to get this page. Now, for that, because we have to replace this an existing page. So, we need to do a page fault to get this page. Then we need to replace an existing frame, because it does not have enough frames in memory. All its pages that are there in its frames are in active use. It needs to replace an existing frame, but because all these pages are in active use, it quickly needs to replace the frame back. It is replacing a page which is in active use to get the page that the page that it immediately needs. To get a page that is not there in main memory and it immediately needs, it is replacing a page which is also in active use. Now, because this page in active use, very quickly in future, that page which it has replaced and put in secondary memory will be required again, and this will lead to low CPU utilization, because the process will be spending more time in servicing the page faults. This will lead to low CPU utilization. The operating system, and another problem is that, especially for early operating systems, this was a grave problem, that the operating system may be thinking that it needs to increase the degree of multiprogramming. Why? Because the CPU utilization has reduced. Why has the CPU utilization reduced? Because processes are doing page fault servicing more than it is executing. And why is that so? Even if, let us say, we are using a global replacement algorithm, one page does not have enough pages in memory, and therefore, it is continuously doing a page fault, and when it is doing a page fault, it may be encroaching into frames allocated to other processes, reducing the number of frames allocated to those processes. Moreover, what happens is that the IO processor remains busy servicing page faults. So, when other processes, even if other processes have enough frames in memory, whenever it requires a page from the secondary storage, it has to wait, because the other process has completely consumed the IO processor. Suppose I have a process P1 which is continuously doing page faults because it does not have enough frames in memory, and I have process P2 which for which it has enough frames and to keep its active pages. This one P2 has enough frames to keep all its active pages in memory. P1 does not have enough frames to keep all its active pages in memory. P1 does not have. Now, P1 is continuously doing a page fault, and in doing so, it is keeping the IO processor busy. Now, when P2, whenever it requires one page and it does one page fault, it will find the IO processor busy, because P1 has completely consumed the IO processor, and therefore, the performance of P2 is also going to reduce. Now, in this way, the whole CPU utilization, the execution in the CPU is going to reduce, because everybody is waiting for some of its pages to be brought from secondary memory. All processes in memory are waiting for some of its pages to be brought from secondary memory, because the IO processor is busy. Now, if the operating system fails to understand this situation, when it sees the CPU utilization low, it may think that it does not have enough processes in main memory to execute in the CPU. So, it will push in another process into the main memory by increasing the degree of multiprogramming. When one more process gets into the main memory and it tries to co-execute, it will also encroach into frames allocated to other processes. It will take away frames allocated to other processes, and the performance of the system will further degrade. So, another process when added to the system will further degrade the total performance of the system, and the CPU utilization will dip further, because of two reasons. Because the new process will again ask for pages from secondary memory, and also other processes for other processes the number of frames allocated to them have reduced, because the new process have to be given a minimum number of frames. So, due to both these reasons, the CPU utilization is going to reduce further, and therefore, the CPU utilization will finally plunge. So, what is the formal definition of thrashing? When a process spends more time swapping pages in and out of memory than actual execution on the CPU, we say that the system is undergoing thrashing, or the process is undergoing thrashing. When a process spends more time in swapping pages in and out than actual execution on the CPU, then we say that the process is thrashing. The system will also undergo a complete, if this process is thrashing for a long time and the thrashing is severe, it will also degrade the performance of the entire system, as we discussed. Now, so therefore, when we increase CPU utilization, or we increase the degree of multiprogramming up to a certain extent, we increase CPU utilization. Then after that, more the processors will start spending more time in paging than in execution, because there are so many processes are coexisting in the main memory, not enough frames could be allocated to keep the active pages of these processes in main memory. So, when we are increasing the degree of multiprogramming, the number of processes that are co-executing on the CPU are increasing, and all these processes will take a share of the of frames allocated in main memory. So, why? Because each of these processes will be allocated a certain number of frames. Now, therefore, when the number of processes increase, the number of frames allocated to each process reduces. When the number of frames reduces, after a certain time, after a certain increase in the degree of multiprogramming, there will not be enough frames for each process to keep all its active pages. Now, for a given process, when it is not able to keep all its active pages in memory, when the number of frames allocated to a process is not sufficient to keep all its active pages in memory, then the process will start thrashing. When the process starts thrashing, and when more and more degree of multiprogramming increases, more and more processes starts thrashing, and this will finally bring down the entire performance of the system, which means that the CPU utilization will reduce. CPU utilization meaning the percentage of time that the CPU is spending in executing instructions. So, that will increase up to a certain extent when the degree of multiprogramming is increased. Why? Because up to this case, I am keeping more processes, and therefore, I am keeping more processes in memory, and I am utilizing the CPU to a higher extent, because more number of processes are there. So, even if some other processes are being suspended for memory, IO, etc., whatever, some other processes will be there for utilizing the CPU, and the CPU will be efficiently sharing itself multiplexing itself among all these processes. But after a certain extent, the number of frames allocated to each of these processes decreases, and then thrashing starts and the CPU utilization plunges. Now, you cannot say that using any such model, you cannot say that a certain fixed number of frames is sufficient for a given process. Why? Because the active pages that a particular process requires is going to vary. Why? Because depending on the locality of reference for a process will vary depending on what it is doing at a given time. Now, for example, let us say at a given time it is continuously within a loop and is executing a certain set of instructions and a certain set of data it is operating on a matrix. So, it requires a certain number of pages for that matrix, and a certain number of pages for the instructions within that loop. So, let us say that at a given time a process is executing a loop. So, this loop contains a set of instructions, and let us say in this loop it is executing on a matrix. So, if I am able to keep enough frames, enough pages, if I have enough frames for this process to keep the pages of this matrix that are actively being used and enough pages for the instructions in the loop, then I will not suffer a lot of page faults. However, if I am not able to keep if the number of frames are not sufficient to keep the data corresponding to the matrix or the data corresponding to the instructions in the main memory pages, if I do not have that many sufficient number of frames, then there is going to be a lot of page faults, possibly leading to thrashing. Now, this if now the program comes out of this loop and does something else, the requirements of its active pages corresponding to data as well as for instructions is going to change. So, therefore, over time a program's characteristic in terms of the active pages that is required is going to change, and this is captured by something called the working set model. So, for the working set model, we first define a working set window. A working set window is a fixed number of page references in the past. Let us say you look at 10,000 page references in the past. So, delta equals to 10,000 instructions in the past. Okay. So, WSI is the working set of process I. Let us say WSI is the working set of process I. It is defined as the number of distinct pages referenced in the most recent delta references. So, let us say these are not 10,000 instructions, but 10,000 references. So, in the last 10,000 references, how many distinct pages were referenced? This will be called the working set of the process. For example, let us say that this is the sequence of references for a given process. Now, if the working set delta equals to 10, then at time t1 I am going to look at the last 10 references, and I want to find out how many distinct pages were referenced in the last 10 page references. For this case, the number of distinct pages that were referenced in the last 10 references are 1, 2, 6, 5 and 7. So, 1, 2, 5, 6, 7 are the distinct pages referenced in the last 10 references. So, I say that the working set of this process is 5, which is a measure of the number of active pages that it requires at this point in time given a working set window delta of 10. Now, let us say after a certain amount of time at time t2, this is what happened at time t1. Let us say now at time t2 what has happened? The characteristic of the program has changed. Now, the program is doing something else and it is continuously referencing pages only 3 and 4. So, in the last 10 page references at time t2, what is happening is that it has the unique or the distinct pages that it has referenced is only 3 and 4. So, the working set at time t2 is 3 and 4, while the working set at time t1 is 1, 2, 5, 6, 7. So, the demand for pages varies depending on time and is defined and is roughly defined by the working set at a given time. Now, if this working set delta, working set window is too small, it will not cover the entire locality of a process. What do we mean by the locality of a process? By the locality of a process, we will mean at a given time what is it doing and what are the active pages it is referencing. That will define the locality of the process. Now, if the delta is, if this value of delta is very small, it will not cover the entire locality of the process. So, let us say even if delta says that it requires the working set size is 5, and if you then keep 5 frames for it, it will still encounter a lot of faults, because it has not covered, delta is so small that it has not covered its entire locality. On the other hand, if delta is too large, it will encounter multiple localities, and then I will uselessly allocate more frames to this process than it actually requires, maybe at the expense of other processes, okay, because other processes will possibly not get enough frames, may not get enough frames. So, if the total demand for frames demand D will be given by the summation of the working sets of all processes, and we can say that the system will be thrashing if the total demand is greater than m, which is the total number of frames available in my main memory. If the total demand for frames, which is basically roughly defined by the working set of the processes, as we said. So, if the total demand, which is the summation of the working sets of all processes, is more than the total number of frames available in main memory, the system is going to experience thrashing. So, what do you do when the total demand is greater than the number of processes that you have? You suspend or swap out one of the processes. So, you go on suspending processes until you have sufficient number of frames for each process. Possibly you will suspend the low priority processes to start with, to allow high priority processes to have better performance. Now, working set size has been a very successful model, but a more direct approach is to directly work on the basis of what is the page fault frequency that a particular process is currently experiencing. Working set size is a fine model, but a more direct approach than working set size is to measure the page fault frequency at a given time, and to establish at a given time for each process to have an acceptable page fault frequency for each process. For example, the page fault frequency for a low priority process, the acceptable page fault frequency for a low priority process may be higher than the acceptable page fault frequency for a high priority process. However, for each process we can set an acceptable page fault frequency rate. Okay. So, establish acceptable page fault frequency rate and use local replacement policy. If the actual rate is too low, the process loses frames, we deduct frames from this process. So, if the page fault frequency for a process is lower than a given threshold, that means what? It does not require frames allocated to it. Then we can take frames from this process and give it to somebody else. So, if the actual page fault frequency rate is very low, the process loses frames. We take frames from this process and give it to other processes. If the actual page fault rate frequency is very high, then the process gains frames. If the actual page fault frequency is very high, it means that this process possibly does not have enough frames to keep all its active pages, therefore, it needs more frames for it. Now, it can be given from other processes to it. So, this figure shows this, that for a process I have an acceptable upper bound and I have a lower bound. If the page fault frequency decreases than this lower bound, what we do is that we decrease the number of frames allocated to this process. When the page fault frequency for this process is higher than this bound, that means the process is experiencing more page faults than it is supposed to. What we should do is we should increase the number of frames allocated to this process, so that it can keep more active pages in it, and this is how it controls page fault frequency. With this we come to the end of this lecture.